in today's talk, I will be presenting some preliminary ideas on uh, possibly making a case for virtualizing the electric utility in cloud data centers. And the meaning of what we are proposing to virtualize will becomes clear soon. This is joint and ongoing work with Wang, who's my graduate student, and with my colleagues George Kesidis, Uday Shanbhag, and Qian Wang, all from Penn State. So it's quite well known that powering data centers is quite expensive. So this is a figure that is presenting and comparing key components of the cost in building and then running a data center. And this is based on sort of trends and ideas presented in a very well regarded book on the topic of data centers by Barroso and Holtzle from Google. Now the actual numbers might vary from data center to data center depending on many factors. So I'm not going to sort of go into the details of how this was done, but the key takeaway for our purposes here is that the cost of building the IT infrastructure, which is labeled as servers here, that is often comparable to the cost that is incurred towards building the power infrastructure, the highly reliable power infrastructure that is needed to keep these servers powered on. And the same applies to the utility bill that the data center has to pay for example, on a monthly basis to the electric utility company. So both the operational expense part, the OPEX, and the capital expenses or the CAPEX, they are sort of the same order as the cost of the IT itself. So the focus of this talk will be the OPEX part. Okay? This is typically the utility bill paid on a monthly basis by the data center. So we all know that a lot of work has gone in the past, perhaps a decade, in trying to optimize the utility bill by making data centers more power efficient. The focus of this work is on a complementary problem which has perhaps received less attention, which is how should the data center recoup these costs from its tenants? It's easy to see why this might be an important problem in a public cloud, for example, for reasons related to fairness. In less direct and implicit or more implicit ways, this is likely to be a problem of importance even in private clouds. So let's first try to develop a simple picture of how this is done today. And then I'll sort of present some arguments about what might be wrong with it. So the interface that clouds present today to their tenants is basically purely IT based. Okay, so if it's an infrastructure as a service cloud, it sells virtual machines or storage capacity in the unit of bytes or IO bandwidth in the units of bytes per second perhaps. If it's a software as a service cloud, it might offer software constructs like queries or sessions and then price these. So this table presents some examples of VMs and bytes transferred and bytes stored and their prices as offered by some popular infrastructure as service clouds. Of course, the actual interfaces are even more diverse and there are lots of varieties, but the key point holds that all of these interfaces are in units of virtualized IT resources. Okay? If we compare this with how electric utility companies price the resource they are selling, i.e. power, right? We'll find that is very different from how clouds price the resources they are selling. Well, I'll resist the temptation of creating jokes around that. So I was saying that um, how are the energy-related costs sort of passed over to tenants? Essentially, energy-related costs are bundled into the prices that the cloud provider associates with these IT abstractions, right? And that is done without considering important idiosyncrasies of electricity pricing. Okay? Also, without considering idiosyncrasies of performance-related idiosyncrasies for different kinds of tenants. So our focus will be on the first kind of sort of features, which is idiosyncrasies of electric utility pricing. Okay. And I will use one particular form of electric utility pricing, which one might call peak-based pricing, to make my point. I should note that there are other kinds of complex pricing schemes that also exist, such as tiered pricing or real-time pricing, and many variants within them. And many of the problems that I'm sort of going to point out perhaps apply to them as well. But I'm going to sort of restrict my attention only to this particular form of utility pricing. So as small consumers of electric power, perhaps as homeowners, we are used to thinking of our electric bill that we get at the end of a month perhaps as follows. Okay? So we power various appliances, we consume a certain amount of energy over a month, and then at the end of the month, that raw amount of energy that we consumed is multiplied by some number, let's say 5 cents per kilowatt hour or 7 cents. Perhaps that is time varying, and that sort of creates what is sent to us by the electric utility. Okay. Well, for large consumers of power, like data centers, electric billing works quite differently. Okay? So they do pay for the raw energy that they consume over the month, similar to how smaller consumers pay. But in addition, there is a charge, an additional charge they pay, which is dependent on perhaps the peak or some other aspect of the variance in their demand. Okay? So which means that for the same amount of raw energy consumption, if your power draw is more bursty or has a higher peak, then you can expect to see a higher electricity bill. Okay? So let's try to understand that more clearly using this figure here. So I'm showing the power draw of a hypothetical data center over a period of, let's say, a month. So the x-axis is time, and the y-axis is showing its power draw, let's say, in watts. So the area under the curve is obviously the raw energy consumption, and a part of the electric bill will be made up by multiplying this by some energy charge, let's say 5 cents per kilowatt hour in my example. Okay? So in addition to this, the electric utility will also keep track of the peak power consumption, which is highlighted in that figure, which will be multiplied by another factor. So in this example, $12 per kilowatt. So notice the difference that the two have different units. Okay? The second one is in terms of dollars per kilowatt. Okay? So what is the impact of that? As I said, if you have a high peak for the same raw energy consumption, if you have a higher peak compared to someone else, you will pay a higher electricity bill. So just to understand the magnitude of that, for the pricing parameters that I described, 5 cents per kilowatt hour for the energy charge, and $12 per kilowatt for the peak power charge, which are simplified sort of parameters derived from Duke Utility Company. If your power draw has a peak to average ratio of 3:1, then half of your electricity bill will be contributed by the peak component, the peak that I described. Okay? So that suggests that this feature of electric utility pricing can contribute significantly to a data center's electricity bill. Okay? And so we should be thinking carefully about how this should be passed on to the tenants. Okay? So the previous discussion should make it clear that there exists a big gap between how electric utility companies price their resource and how they charge data centers on the one hand, and how data centers charge their tenants. Okay? And using somewhat simplified examples in the next few slides, I'm going to argue that this gap can result in at least two kinds of shortcomings. Okay? The first kind of shortcoming relates to what one might think of as a lack of a certain kind of fairness fairness in how tenants get charged for their usage. And the second kind of shortcoming relates to a loss of cost efficacy or profitability in the operation not only of the tenants, but of the cloud itself. Following this, I will consider some simple and intuitively appealing ways to fix these problems. And I'll use them to show why fixing this problem is not trivial. Okay? The intuitively appealing approaches may not work, which will lead us to our proposal of virtualizing the electric utility. And again, the meaning of that will become clear when we get there. Okay. So let's carry out a simple thought experiment to understand the first kind of shortcoming, which relates to the issue of fairness. So in this example, we have the ecosystem shown in the slide. So we have a cloud in the middle, which has made investment into its IT infrastructure and the power infrastructure. It's procuring power from some electric utility company based on a peak-based contract, also shown in the figure. And let's assume it has 2 tenants. So it's selling, let's say, virtual machines to 2 tenants. Let's call them tenant 1 and tenant 2. Now let's construct a special sort of stylized powered resource demand profile for both of these tenants. Okay? So let's imagine that over, let's say, a period of a month, the 2 tenants pose virtual machine demands as shown in the figure. Okay? So you will notice that they have the same average virtual machine demand. Okay? Let's assume that they have the same average virtual machine demand, but there's a difference between the variance of their demands. So the tenant 1 has a relatively steady demand over the month, but the second tenant has a higher peak. Okay. So the energy demand, the power demand posed by the cloud as a whole on the electric utility is obviously is going to be the summation of the power consumption corresponding to these, the summation of these VM demands, shown by this figure here. Okay. So the cost now that the data center will now want to pass on to the tenants under a simplified assumption of revenue neutrality, which might apply to a virtual cloud, would be the summation of the virtual machine cost investment that it has made on on behalf of these VMs, plus the electric utility bill that results from the resource usage of these VMs. Okay? So that's V plus C in the notation that I'm describing. If we think about how that's done today, both the tenants will see an identical bill of V plus C over 2. Okay? But I hope many of you will agree that something unfair has happened here from the tenant 1's perspective. Okay? If you look at a part of this electricity bill, which is made up by the peak charge, clearly tenant 2 contributes more to it than tenant 1, possibly much more. Okay? So if you consider that unfair, then that's sort of the problem that I'm identifying here. Okay? So if we would like to do something so that this unfairness is removed. So let's look at some sort of simple possibilities that come to mind. Okay? So one thing that we might sort of identify here is, well, rather than doing things the way they are done today, perhaps we should be passing on something resembling the utility pricing structure onto the tenants. Right? For example, we might want to think of an approach that passes on the utility pricing structure, which is a combination of an average charge and a peak charge, as is to the tenants. Okay? So we might base each tenant's peak charge on its local peak. But it's easy to see that that's not going to fix our problem, because consider a scenario where the 2 tenants end up having peaks that are not aligned with the aggregate peak. Okay? This might happen just because that's how the tenant's demand is, or it might happen because tenant 2 being, one of them being clever, sort of shifts its demand and moves its own local peak to a different point in time. Okay? So what's happening here is the charge we are passing on to the tenants, the peak charge, that actually exceeds the peak-based charge that the cloud itself pays to the utility. So this is a different sort of form of unfairness that's arising here. So which allows us to enhance our sort of thought process a little bit. Okay? Not only should we be passing on something resembling the utility pricing structure, we should try to make sure, again, under this assumption of revenue or desire of revenue neutrality, that the tenants are charged for their contribution to the OPEX, okay? Not based on something arbitrary. And the first thought that perhaps comes to mind is, well, let's try to charge tenants for their peak usage based on their contribution to the actual aggregate peak. Okay? And if we consider a pricing scheme like that, that allows us to think about a different kind of shortcoming which pertains to cost efficacy. So I'm going to sort of, in the interest of time, I'm going to not go over the simple calculation here. But if we bring into the picture the following feature of a tenant that, or at least an intelligent tenant, that it's going to carry out demand response in response to the prices it's shown, then it can be shown that a scheme of the kind that I was describing in the previous slide may result in the cloud accruing a revenue which is suboptimal. Okay? So there is perhaps a classic fairness versus efficiency kind of tension that this brings out. So let me just skip this over. Okay? So the problem is you could be operating in regimes where there is an unfairness problem, or you might be operating in a regime where you are not cost effective. Okay? So in addition to the previous sort of features I identified, we would also want the prices that are passed on to the tenants to reflect the idiosyncratic value that the tenants derive from power. Okay? And based on previous research about the diversity of the power and performance relationships across different kinds of tenants, we know that different tenants do derive and associate different amounts of value to power. Okay? So when we start talking about sort of quote-unquote value, arguably the best judge of this value is the tenant itself, not a cloud. Okay? Meaning it should be the cloud, it should be a tenant who should sort of make this decision of, well, how much value am I going to derive from power that is priced in a certain way, not the cloud doing it on its behalf. Okay? This should sound similar in spirit to ideas in networking and operating systems, where people have, for example, talked about building exokernels which do the bare minimum resource management and protection and let applications carry out a lot of resource management decisions on their own, depending on their properties. Okay? So that leads us to come up with this idea of virtualizing the electric utility. Okay? So this is sort of related to the notion of virtualizing power, treating power as almost a first-class resource, which others have talked about. Okay? But this is sort of taking it a step further and saying that, well, at least for big tenants and long-lasting tenants which might be viewed as mini data centers unto themselves, perhaps it makes sense to make them feel as if they are not only procuring a virtualized data center, but they are interacting with a virtualized electric utility, which might have pricing parameters which the tenants themselves negotiate as per the value that they derive from the utility. Okay? So let me just show you a pictorial depiction of what such a system might look like. So if you compare this with the previous picture I had shown you, this cloud actually makes its tenants feel as if they are running in their own data center, along with interacting with their own electric utility providers. Okay? A cloud such as this would have to create a virtualized electricity meter so that the tenants can sort of look at power consumption arising out of their respective resource usage. Okay? So this is showing that, so that's sort of figure is showing some of that. You could go crazy with this idea and also sort of say, well, you might also want to expose some of the features like renewable presence and so on onto the tenants and let them sort of decide who wants to be greener than the other one. Right? So that's sort of the basic idea. And if one agrees with this proposal and if it makes sense, then there are two kinds of problems that would be worth addressing here. One would be a mechanism design problem, which would involve coming up with ways in which tenants and cloud provider can negotiate appropriate prices, mutually agreeable electric pricing structures between them. Okay? This would, just like how such negotiations operate on the course timescale of perhaps months between actual clouds and electric utilities, this would probably operate on the course timescale of months. Okay? And the other kind of problem would be a fine timescale control problem that these tenants would solve to optimize their profits. Okay? And these control problems would be arguably significantly more complicated than the control problems that are solved today, because today's problems are solved only by considering the trade-offs between IT resources and the costs and value that they offer. Okay? There would be an additional complication because of the presence of power-related costs and power performance trade-offs. So let me just jump to, so that's, those are the two kinds of problems that we envision working on in the future. So with that, let me just quickly conclude. So I try to describe the gap that exists today between electric utility pricing on the one hand and how cloud systems price their resources. I argued that that can lead to problems related to unfairness and lack of profitability for the cloud. I argued that tenants are likely to be the best judges of the value they derive from power, which might motivate us to consider not just virtualizing power as has been done in the recent past, but virtualize even the pricing scheme, and perhaps more. And I quickly sort of described some challenges that would arise in such an ecosystem, the kinds of problems that one would want to solve. With that, I'm happy to take any questions.
Phil Gibbons, Intel Labs. So to me, it looks like the main challenge here is the peak pricing model, because there's so many ways to game that, right? I mean,
yeah.
if you're only going to be charged against your contribution to the peak, then your goal is to always make sure you're being the second highest, right? That when you demand all your resources, it's never at that instant that it's the peak for the month. So it seems like that's
just
sort
to
of
make
artificial creation of the peak pricing model, which I guess is the existing model. But the second thing is that
let me just make sure that the way you described it is actually what is actually the kind of pricing scheme I was describing. So the peak is not dictated by a particular time that the electric provider is choosing. That is another possibility, and there are tariff schemes that do that. The peak is purely determined by the behavior of the consumer.
Sure. But I'm just saying
so
that.
are we in agreement?
Yeah.
Okay. Yeah. Just making sure.
That's fine. It's just so easy to game that, right? That basically,
right.
I mean, you know, as long if you're only getting charged for your contribution to that point in the month that happened to be the peak,
right?
Then just avoid that, right? You could be the second highest any other time. You're consistently the second highest.
Right.
But
exactly.
anyway, the second point is that the energy pricing is actually a market, right?
Yeah.
And when you hit a peak actually matters, right? There's times when energy is a lot more expensive and times when it's less expensive.
Yes.
So if you're in a world, if your view of the world is that there's a market, so there's an instantaneous price for every little bit of power, then a lot of these problems actually go away, right? Because then I know it has nothing to do with this weird formula that's going to hit me at the end of the month or hit the provider at the end of the month. It's going to be instantaneous. I'm going to know that if I want to draw this much more power as a tenant at this particular moment in time, it's the middle of a hot summer day. It's going to cost me more.
Right.
And don't a lot of these problems just go away in that?
So
model?
again, let me make sure that I understand this correctly. So there are in the ecosystem I described, there are two kinds of interactions going on. One between the actual utility and the cloud itself, and the other between the cloud and its tenant, or the virtual electric utility and the tenant. So are you saying that if the pricing scheme used by the physical electric utility were real-time based,
yes,
then these problems would go away?
That's what I'm wondering, yes.
No, it doesn't, because that's a slightly more complicated argument to make, but there are problems related to unfairness and cost efficacy that can arise even there. Perhaps what you're suggesting is in a real-time based pricing market, the cloud would just pass these as they are to the tenants.
Yes, you
right?
still let the tenants decide the
Right.
value.
But then
You're-
using simple modeling, one can show that, again, that may not be the cost optimal thing for the cloud to do, just because different tenants are going to derive different values from the same amount of power and the same amount of payment that they make to the power. So imagine the following scenario where the cloud provider is sort of buying a real-time priced
Right.
asset, and it's also coming up with real-time prices for tenants. So you can show that there are scenarios where the prices that it's passing on to its tenants are not exactly the same as what it's paying to the electric utility.
Okay.
Does-
Maybe
does-
I'll talk to you offline about that, because
Yeah.
it seems like you just pass it straight along and let the tenants decide.
The basic problem with passing it straight along is that there might be two tenants who price it differently. I guess, okay, so one thing I didn't mention is if you also want to think about how the tenants will possibly react to that price. And there are differences across tenants in how they react to different prices.
I see. All right.
We can talk more if you like.
Hi, Dan Schatzberg from Boston University. You made this analogy to exokernels,
Right.
and one of the challenges there has been that when you lower the abstraction, that it makes it more difficult to do aggregation, and intuitively it seems like you have the same problem here, that one of the advantages of cloud computing is that there's so much aggregation being done to give everyone better value that perhaps you may lose all your win by virtualizing the power consumption.
So I didn't quite, could you make that more explicit, the value of aggregation? Because I didn't quite follow.
That, you know, rather than saying everyone's going to make a decision based on power, they make their own decision based on number of bytes they read.
Right.
And I, as the provider, will find a clever way to mitigate the power cost of that and give everyone a lower price
Right.
across the board.
So
rather
just to
than-
make sure, I did not suggest that the existing interface be replaced completely by an interface that argues only about power. I'm actually arguing for augmenting the current interface. So in the model that I was describing, a tenant would still see an interface like today's, where they would be able to buy bytes or virtual machines and so on. But additionally, if they so wanted, they would also be given information about the power consumption they are causing,
But to,
in addition to a pricing scheme that they would have negotiated.
But to make that accurate, don't you have to avoid some of the aggregation and sharing that naturally happens?
No, yeah, clearly. So there would be some significant challenges in actually making it happen. One of which is a lot of the power consumption happens because of things which are shared across different tenants, and separating it out, meaning properly accounting that, is indeed a difficult problem. There's been some work on that, and I think the previous talk sort of talked about something which relates to it. But that would be a significant problem that one would have to solve.
Okay, thank you.
Sure.
All right, thank you, Bhuvan.